Welcome back to the deep dive. Today the subtitle is Time, Motion, and Dynamics. So we're basically stopping the snapshot and pressing play.
We're talking about BPS geometries,
Right. We're watching these things evolve.
which is where the trouble really starts. Because in this specific corner of physics, time isn't just the ticking of a clock. It's something much, much more slippery.
That's actually the first big claim in the source material, isn't it? Right on the second slide. It says time is not merely linear progression. That just feels like a philosophical curveball to start a physics discussion with.
It is.
If time isn't linear here, what is it?
So in this context, it's really defined by three things: motion, thermodynamics, and
Attractor mechanism.
think of it this way. In our daily life, time passes, even if you sit perfectly still. In these BPS geometries, time is the change in the system. If nothing moves and nothing heats up, time effectively, well, it doesn't exist.
The document mentions geodesic evolution. That sounds incredibly impressive, but let's break that down for everyone. What even is a geodesic?
Right, a geodesic is just the most efficient path across a curved surface.
So not a straight line.
Not on a flat map, no. If you're flying from, say, New York to London, the geodesic isn't a straight line on that map. It's a curve over the globe. Here, the motion isn't a plane. It's the entire system evolving along the most efficient path through this incredibly complex, multi-dimensional shape they call a moduli space.
You know, that's a term that keeps popping up in these papers. Give us the non-textbook definition.
The non-textbook definition.
Hmm.
Okay? Think of a moduli space as a map of possibilities.
A map of possibilities. I like that.
Every single point on that map represents a different configuration of the universe we're studying. So motion, in this sense, isn't a car driving down a street. It's the system just drifting from one possible configuration to another across that map.
Okay, so motion is geometry. But the document also ties time to thermodynamics. It explicitly links entropy and temperature to time flow.
And this is the second pillar. Evolution is strictly time-oriented here because it involves heat. The source makes a really bold claim. Without thermal change, without the emission of energy or light, the whole concept of forward time becomes meaningless.
So things only move forward because they get messier. They generate entropy.
That's the idea. So if you have a perfectly ordered, cold system, time stands still. It becomes static. And that brings us to the third and probably the most mind-bending pillar on this slide, the attractor mechanism.
I spent some time trying to get my head around this section. It describes the attractor mechanism as a proxy for time flow. What does that even mean?
This is absolutely crucial for understanding the black holes we're going to get to later.
Yeah.
Imagine you roll a ball into a really deep valley.
Okay.
It doesn't matter if you drop the ball from the north, south, east, or west. Eventually, gravity pulls it to the exact same spot at the very bottom.
So the destination is fixed no matter where you started.
Exactly. The attractor mechanism does that for quantum fields.
Yeah.
It drives them toward fixed values. It sort of wipes out the history of where they started and forces them to a specific destiny. And in this system, moving toward that destiny, that's what we call time.
That is weirdly fatalistic. But okay, let's zoom in on what is actually moving. The next section introduces monopole evolution.
Right. So we're shifting from the landscape to the objects actually in it. We're looking at quantum dynamics.
And it mentions zero modes. It sounds like a setting on my washing machine, but I'm guessing it's not.
Not quite, no. In standard physics, a particle has a position. In this supersymmetric quantum mechanics, or SQM as they call it, things like position, orientation, and charge are collective coordinates. They define the state itself.
And they're called zero modes because
They're the low-energy ways the system can change without, breaking apart.
But the document suggests they do sometimes break apart. There's a term here I circled, wall crossing. It mentions walls of marginal stability. That sounds precarious.
It is a fascinating phenomenon. Imagine you have a composite object, say a cluster of particles held together. As you tune the parameters of the universe they live in.
So moving across that map of possibilities we talked about.
Exactly. As you move across that map, you might hit an invisible wall.
And at that wall, the rules just change.
The binding energy drops to zero. All of a sudden, the object can just fall apart or completely reorganize. The math shows that even though the underlying numbers change smoothly, the physical object undergoes this sudden metamorphosis. It just snaps into a new form.
Like water instantly snapping into ice because the temperature dropped 1 degree.
That's a perfect analogy. The indices, the numbers describing it, change continuously, but the physical reality just jumps.
And that brings us to how these things actually interact. The document has this great section titled Interaction is Geometry. This was a real light bulb moment for me.
Hmm.
I usually think of interaction like billiard balls smacking into each other. But this shows a hyperkähler manifold and something called an Atiyah-Hitchin metric.
This is the elegance of the theory. Instead of two particles bumping, think of a single point moving along a curved surface. The shape of that surface is the force.
So it's like Einstein's gravity. The curvature of space tells matter how to move.
Precisely. Look at the 90-degree scattering example in the notes. If two of these molecules head toward each other head-on, they don't just bounce off randomly.
No.
The geometry of the space, that Atiyah-Hitchin metric, it forces them to turn exactly 90 degrees. It's not a choice. It's just the shape of the road they are on.
But there's a catch. The source material calls this an approximation. And then later there's a whole slide called the reality of scattering that seems to walk it all back.
Ah, yes. The reality check. Everything we just said, that perfect, smooth, geometric sliding that all assumes things are moving slowly.
And if they speed up?
Then the math gets messy. The document notes that at high velocity you get emission. The system starts radiating light in Higgs scalars.
It says the radiated energy scales as velocity to the power of 3 or 5. That seems like a massive jump.
It is. It means if you go just a little bit faster, your energy loss skyrockets. It's like taking a sharp corner in a car. Do it slowly. It's smooth geometry. Do it at 100 miles an hour. You get screeching tires, smoke, heat. That's the radiation. You fall off the perfect geometric path.
So the whole interaction as geometry idea is only true if you're, what, driving carefully?
Exactly. It's a leaky geometry at high speeds. The energy bleeds out, and the clean, beautiful lines of the theory start to blur.
Let's talk about what these things actually look like. We've been calling them monopoles, but this section on quantum superposition shows these glowing geometric shapes, Platonic monopoles.
Yeah, we have to stop thinking of these clusters as like little rocks or little balls.
Yeah.
They are wave functions. They are probabilities.
A quantum blur.
A quantum blur, yes. A Platonic cluster might look like a tetrahedron, a pyramid, but it's superposed. It's shifting between different shapes all the time.
And then there's the term magnetic bags, which frankly is a great band name, but what does it mean here?
It describes what happens when you have a huge number of these charges. They stop looking like individual points and start behaving more like a bag or a halo, a solid cloud of uniform density.
But are these bags stable?
Not always. That's the thing. The document notes that some of these beautiful symmetric shapes are actually intermediate, unstable states. They appear in the math, they shimmer for a moment, and then they resolve into something else.
Okay, let's move on to something that is definitely not a ghost. The heavyweight champion of this document, black holes.
Right. This is where all this math really pays off. We're looking at what's called the throat geometry.
It shows this funnel shape, and it talks about emergent symmetry near the horizon.
Think of a black hole as a chaotic blender on the outside. It's ripping things apart, it's all very messy. But as you go down that throat toward the event horizon, the document says the geometry factorizes. It becomes perfectly symmetrical.
And this brings us back to that attractor mechanism.
It does.
I wanted to circle back to that because the slide here says, scalar fields are driven to fixed values at the horizon, independent of their starting point.
This is forgetting. Imagine you throw an entire library into a black hole. The information, all the specific details of those books, it gets washed away as far as the geometry is concerned. By the time you reach the horizon, the value of the fields is fixed purely by the charge of the black hole.
So the black hole just doesn't care what you threw in. It forces everything to match its own internal logic.
It forces a specific destination, a universal horizon value. An incredibly powerful concept that the geometry deep inside that well is universal no matter what the chaos is like outside.
But if it's that powerful, why doesn't it just crush everything to a singularity? There's a diagram here on stability. It looks like a tug of war.
And this is the magic of BPS states. You have magnetic attraction pulling everything in, that's basically gravity, but you also have Higgs scalar repulsion pushing out.
And in this specific case, they are equal.
In what's called the BPS limit, they cancel out exactly. It's a perfect cosmic stalemate. The document describes the throat itself as a space-like barrier. The shape of space is literally holding the roof up, preventing the black hole from collapsing on itself.
That's incredible. The geometry itself is the structural support, but here's where I got a bit confused. The document defines the mass of the black hole using the vacuum ad infinity.
Right, the ADM mass.
So it says the mass depends on the boundary way out at the edge of the universe. But we just said the black hole forgets the boundary. Isn't that a contradiction?
It is, and it isn't. It's a duality. That's the tension the document is highlighting. From the outside, looking at the black hole from a safe distance, the mass you measure depends on the environment at infinity.
Okay.
But from the inside, right at the horizon, the black hole is universal. It completely ignores infinity.
So it has a public face and a private soul.
That's a very poetic way to put it.
Yeah.
And that private soul, the horizon area, is directly linked to entropy. You see the formula there, S equals A over 4.
Which leads us to temperature. The document talks about extremal black holes being at 0 temperature.
Absolute zero, frozen. These are the static states we talked about at the very beginning. There's no Hawking radiation, no heat. They are like a crystal lattice, just perfectly ordered.
But then we have the thawing. What happens if you add just a tiny bit of mass?
Well, see, you can't add just a tiny bit. The document mentions a mass gap. You actually have to add a minimum chunk of energy to wake it up.
Like kickstarting an engine. You can't just trickle fuel in.
Exactly. In supergravity, you can't just drizzle energy in. You need a specific quantum of energy to bridge that gap. But once you jump it, the black hole thaws. It becomes thermal.
And the throat changes?
The throat stops being infinite and becomes finite. And suddenly, it starts to emit Hawking radiation. It comes alive.
This leads to the finale, right? The microscopic origins. This feels like the why does any of this matter section. It references string theory and a specific paper by Stromer and Waffe.
This is the victory lap for the theorists. For decades, we had Einstein's formula for black hole entropy area divided by 4. Simple enough.
What did it mean?
Exactly. In physics, entropy means hidden information or microstates. If you have entropy, you must be counting something. Imagine a messy room. The entropy is just a number of ways you can arrange the mess. But in a smooth, empty black hole geometry, what are you counting?
Einstein's theory couldn't say, it just gave the number.
Right. It was a formula without a source. But then Strominger and Waffe, who are cited here, used string theory. They model the black hole not as a smooth pit, but as a collection of D-branes and winding strings.
And they counted the strings.
They counted the number of ways you can wrap these strings and branes around the hidden dimensions.
Yeah.
It's just a pure counting problem. And when they did the math,
Let me guess. It matched?
it matched Einstein's A over 4 formula. Exactly. This was the proof that black holes aren't just empty geometry. They're complex quantum objects packed with strings. It linked macroscopic gravity to the microscopic quantum world.
That connection between the giant black hole and the tiny string, that's what this whole thing has been building towards.
It is. It's the bridge.
Yeah.
We needed the thermodynamics, the entropy, and the geometry to build that bridge.
So to wrap this all up, the document summarizes the state of the system in 3 points. First, dynamic stability. Things look frozen, but are actually teeming with quantum life inside.
Exactly. It looks like a statue,
Yeah.
but inside it's a beehive.
Second, geometry as interaction. All those forces are just the curvature of the map.
The train dictates the path.
And third, that bridge we just mentioned.
Thermodynamics linking gravity to strings. It's the unification of the very big and the very small.
You know, I just keep going back to that attractor mechanism, the idea that the universe has these fixed points, that no matter how messy the start is, if you fall into that gravity well, you end up at the exact same destination.
It challenges our intuition, doesn't it? We think history matters. We think where we come from determines who we are. But inside these BPS geometries, the horizon doesn't care about your history. It only cares about your charge. It imposes a universal outcome,
A physical form of destiny.
written right into the geometry itself. It suggests that in some parts of the universe, the end of the story is already written, no matter how the opening chapter goes.
That is a heavy thought to end on. We've gone from neon wireframes to the nature of destiny. Thanks for helping me decode this state of the system.
My pleasure. It's always good to look under the hood of reality.
And thank you for listening. Next time you check the time, just remember, it's not just a clock ticking, it's entropy, it's heat, and it might just be an attractor mechanism pulling you toward the future. We'll see you on the next deep dive.